In this section, we're looking at exponential and logarithmic models. And we've already looked at some of this. We have done, for example, compound interest formula problems. So remember, we could set something like this up in that compound interest formula where we have our principal or amount times 1 plus our rate. And if it's being compounded, that would be the number of times it's compounded per year, and T is our time in years. So let's say your family invests $10,000 the day you are born, and in that account it's getting a rate of 5.5%. It's being compounded quarterly, so we could use our compound interest formula to find what the account balance would be on your 21st birthday. So we have the $10,000 and our rate is 5.5%, so as a decimal value it's 0.055. Compounded quarterly means 4 times per year, so that's 4 times for each of those 21 years. And so we're going to then use our calculator. So we have our $10,000, and that's 1 plus 0.055 divided by 4. And we're raising that to the 4 times 21 power. So that account balance on your 21st birthday would be $31,491.46. Carbon dating is another model that we can look at as a way to date things. So here's an example in your book that talks about organic material and the ratio of radioactive versus non-radioactive carbon isotopes, and using the equation here, knowing that ratio is equal to, and we have our value of 1 over 10 to the 12th times E. Remember, E is involved when we're talking about continuous change. We have E raised to the negative T divided by 8,223, and it's a decay problem. We can see that this is decaying here, and we're told that the half-life of that carbon-14 is about 5,700 years. And because it's so long, that's what allows us to use that to date things. So now in using that model, we are going to take this equation and we can estimate the age of a newly discovered fossil for which the ratio of the carbon-14 to carbon-12 is 1 over 10 to the 13th. So if we're given that's the ratio, to find the age, we can take that 1 over 10 to the 13th and set it equal to, here's our equation, 1 over 10 to the 12th times E raised to the negative T divided by 8,223. So now we're solving for T. I would first multiply both sides by our reciprocal here. So that means I'm going to be multiplying by 10 to the 12th on both sides. Of course, it's going to cancel here when we multiply by 10 to the 12th. And when I multiply by 10 to the 12th here, all but one of them on the bottom is going to cancel out. So we're going to have 1 over 10 is equal to E raised to the negative T divided by 8,223. Our variable is an exponent, so we're going to have to use a logarithm to solve this. Because our base is E, then that would be natural log. So we'll be looking at the natural log of 1/10, and that's going to be equal to our negative T divided by 8,223. So the natural log of 1/10 gives us a value of negative 2.303. And now we'll multiply both sides by, we can get rid of the negative sign here as well. If I multiply both sides by a negative 8,223, then that gives us our years. That's a time of approximately 18,934 years. This last example, we're looking at the spreading of a virus on a college campus. There are 5,000 students, and one returns back from vacation with a contagious and long-lasting flu. The spread of the virus is modeled by the given equation where y is our total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. So the question is, how many days until the college cancels classes? So 40% of the 5,000 students would be 2,000. So if we take our 2,000 and set it equal to our given model, that is the number we're looking for to find out when they will cancel the classes. And so now we're solving for t from here. First, I'd multiply both sides by my denominator. So now I'm going to have our quantity here, 1 plus the 4,999 times e raised to the negative 0.8 times t power. That's times the 2,000. And if we divide 2,000 over to this side, that would give us a 2.5. So now we have 1 plus 4,999 times e raised to the negative 0.8t. Subtract the 1 over and divide by 4,000. If I subtract 1, that's 1.5 and 1.5. And then I'm dividing by the 4,999. Now again, we have a variable within our exponent, so we're going to need to use a logarithm to solve. Our base is e, so that's going to be natural log. Natural log of our 1.5 divided by 4,999 is going to be equal to the negative 0.8 times t. The natural log of 1.5 divided by 4,999 gives us a value of negative 8.11. Divide both sides by negative 0.8. And we find that the time is just over 10 days.